our new material. If we have time at the end, you can come back to your working on your tests. So I just want to point out Project 5 and Quiz 4 are both assigned today, and I just passed them out, so you've got those. Project 5 is due class after tomorrow. I mean, so Friday, not next class, but then following Friday. And then Quiz 4, I can't remember. Why won't this work? Okay, so Project 5. Oh, sorry, it's due Monday. Yeah, it's due. Yeah, not today's Wednesday. That makes sense. Okay. Not next class, but the following. So Project 5 is due Monday, and Quiz 4 is due on our last day of class. It's a short one. Shouldn't take you super long. I didn't want to make it hard, but just to give you a quick assessment on new material before I put it on the final exam. Okay, so Project 5 and Quiz 4 are both due next week. Okay, so we're going to look at a little bit of Chapter 11. So the last material before the final exam. And Chapter 11 is about differential equations. We talked about them very briefly earlier in the semester. So we're going to come back and use some of the techniques we've developed this semester to solve them. So remember, a differential equation is an equation that has derivatives in it, right? It's an equation that involves derivatives of some unknown function. And the solution to a differential equation is a function. So this is essentially different from all the equations that you've solved before where the solution was a number, right? There would be some number that makes it true. Now there's some function that will make this differential equation true. So here are several examples of differential equations. dy dt equals negative t over 2, dy dt equals negative y over 2. dy dt equals 0.02y minus 40,000 e to the 0.03t, or the second derivative of y with respect to t minus 5 times the first derivative plus 6 times the function y itself equals 0. So we're going to solve equation A, right? So equation A is sort of the simplest one, and then we're going to choose, and you get a whole family of solutions. There's a whole family of functions that can make this true. All right, so we go back and look at A. So I'm looking for a function y of t, output y, input t. And I know that because it's dy dt. The derivative of y with respect to t is negative t over 2. So I'm looking for a function whose derivative is negative t over 2. Can you think of a function whose derivative is negative t over 2? Negative t squared over 4. Yeah, that would work. Yeah. And then you can add any constant, right? Any constant, and the derivative of the constant term is 0. So I have a whole family of functions. They're all parabolas that open down, right? And you can just shift them up and down. All of those parabolas satisfy this equation, no matter what c I use. All right, so now I want to choose one particular member of that family. I want to find one specific c value that satisfies an initial value or an initial condition that y of 0 has to equal 3. So I say, okay, well, y of 0, if I put a 0 in for t, I get 0 plus c. That has to equal 3, which means c is 3, right? So that's my one particular solution that satisfies the initial condition. Negative t squared over 4 plus 3. So general solution is a family of functions, and then you have a particular solution that can satisfy an initial condition. Okay, so what does it mean if I'm just telling you that the solution to part B, right, where dy dt equals negative y over 2, the solution is c e to the negative t over 2. That's the general solution. So I want to verify that that's the solution. We don't quite have the techniques to do it, right? This one I was able to do because I only had t's on the right-hand side, so you could just sort of take an antiderivative. But this one I don't really have the tools, so I'm just going to tell you that the solution is c e to the, I can't remember, c e to the negative t over 2. So that's my general solution. It's a general solution because there's a c, this constant, so that creates a whole family of solutions. So what I want to do is show that this equation is true. So I'm going to take dy dt. I'm going to evaluate both sides of this equation and show that they are the same. Okay. All right, so dy dt, if I take the derivative of this thing, what would I get? You get c e to the negative t over 2, right? And then times the derivative of negative t over 2, which is negative a half. Chain rule. Right? Yeah. So if I simplify this, I get negative c e to the negative t over 2 divided by 2. Correct. I used the formula for e to the something instead of the power rule. Yeah. All right, so there's an expression for dy dt. Let's find an expression for negative y over 2. So here's y. If I put in negative y and divide by 2, it's the same thing as dy dt. Right? That's what makes this a solution. When you plug that function in by taking its derivative on the left and putting a negative over 2 on the right, you get the same thing. That's what makes it a solution. Both sides of the equation are the same. I'm getting some blank looks. Okay. Maybe with some more examples, it'll get clearer. Okay. So in each differential equation, I would like to know what the independent and dependent variable is. In all of them, what is the independent variable? T. And the dependent variable? Y in all of them. And you know that by looking at the dy dt, right? The independent variable is always on the bottom. That's the with respect to variable. So in all of these, independent is t and dependent is y. All right, so I'm going to claim that y equals c e to the 2t is a solution to part D. C e to the 2t. So let's verify that. So here's part D. I'm going to say y equals c e to the 2t is a solution. All right, so that means that if I take the second derivative, subtract 5 times the first derivative, plus 6 times the function itself, I should get 0. Right, so I need to come up with the first and second derivative to be able to plug back in here. All right, so y prime is c e to the 2t times 2. Oh, I could have, yeah. Yeah, I definitely could have. I think before I was doing that to try to emphasize that t was the independent variable, right? So this would be 2c e to the 2t, and then y double prime would be 4c e to the 2t. Right? Because 2c is just a constant, so you don't have to do the product rule. You can just carry it along. So my second derivative would be 2c e to the 2t times 2. It's the derivative of the inside. All right, so now this says that y double prime minus 5y prime plus 6y has to equal 0, right? So let's check and see if that's true. If it's true, then this thing that I proposed as a solution really is a solution. We think that that's the solution. So if that's the solution, I should be able to plug all these things in and get 0. So y double prime is 4c e to the 2t minus 5 times y prime, which is 2c e to the 2t, plus 6 times the original function itself, that's c e to the 2t. Does that equal 0? Yeah, this says 4c e to the 2t minus 10c e to the 2t is negative 6 c e to the 2t plus 6 e to the 2t. Yes, it equals 0, which means that that is a solution. Yes, I only know that because I gave it to you. So just like when you first started learning how to do equations in an intro algebra class, the first thing you have to learn is what it means to be a solution, right? It means that when you plug it in, the two sides of the equation are equal. Same thing with a differential equation. Then we'll start developing some techniques on how to find those solutions. Some of them we already can, right? We've just found a solution for A. For B, we would need a little bit more advanced technique. Okay, so there are actually more solutions to part D, right? Not just c e to the 2t, but there are values of r, certain values of r, that will give you a solution to part D for c e to the rt. So let's see, y prime of c e to the rt would be rc e to the rt, and y double prime would be what? R squared, yeah. R squared c e to the rt. All right, so then for this guy to be a solution, it has to satisfy this equation. So it means that if I take the second derivative, r squared c e to the rt minus 5 times the first derivative plus 6 times the original function, I have to get 0. So what if I want to solve that equation for r? Yeah, how do you look at that and see quadratic? Factor out c e to the rt. So every term has a c e to the rt in it, and what I'm left with when I factor that out is r squared minus 5r plus 6. And c e to the rt, that's an exponential function. No matter what you plug in for t or r, that will always be positive, never be 0. So I could divide both sides by it, right? So the only reason we usually don't divide things by variables is because that variable might be 0. But when you know that variables can never be 0, you can divide by them. So all I have left is r squared minus 5r plus 6 equals 0, and that just factors to minus 3 minus 2, and you get r equals 3 or r equals 2. R equals 2 is the one we used before, right? That was the solution we used up here, c e to the 2t. So we knew 2 was a solution. But it turns out that when r equals 3, you also have a solution. So y equals c e to the 3t also satisfies the differential equation. skip the challenge. So the order of a differential equation is the order of the highest derivative it contains, right? So the order is just the highest derivative. So I'm going to look at these A through D examples again. And the order is the highest derivative. What's the highest derivative that shows up in A? First derivative. So in this one, the order is 1. How about in B? 1. Just the first derivative again. How about in C? It's just the first derivative again. The highest derivative is the first. How about in D? 2. There's a second derivative, so the order is 2 on that one. All right, so if you're solving a first order versus a second order differential equation, when you have a first order differential equation, you're always going to have one constant, right? Because when you take an antiderivative, you always have the plus c. For a second order differential equation, you get 2 constants, right? Because you're going to end up taking 2 antiderivatives. So that's sort of why, that's why the c is there, and there was also the r thing to deal with. And there are actually more solutions than just c e to the rt. So that's not the most general solution. So second order differential equations will have 2 constants because you got to take 2 antiderivatives. So first order, 1 constant. Second order, 2 constants in the most general solution. So in general, finding solutions to a differential equation is quite hard. We have a whole course about it, right? But some differential equations can be solved by a technique called separation of variables. If you can take a differential equation and put all the y's on one side together with the dy, and all the t's together on one side with the dt, then the differential equation is said to be separable. Okay, so for equations like that, you can integrate each side of your equation separately to get a solution. So we'll do an example. So we have y of t is going to represent the size of a population at time t. And it's common to model population growth by assuming the population is growing at a rate proportional to its current size, which means the larger the population, the faster it's growing, right? Because there's more, whatevers to reproduce. So if we have a population that grows at a continuous rate of 5% of its population, right? So it's growing at 5% of its population. I want to write that sentence as a differential equation, right? So you are typically used to taking that sentence and writing it as immediately going straight to the function of t using a continuous growth formula. But I want to write it as a differential equation, which means I use the word rate, and that's going to be dy dt. Right? Remember related rates problems from last semester? It's kind of like that. We have to translate it. So our rate, dy dt, is 0.05 times my current population size y. So the rate is 5% of the current population. 5%, and the current population is modeled by the function y. So I've written a differential equation, and I want to solve it by using separation of variables. So that means I'm going to treat the dy dt like a fraction, and I'm going to collect everything with y's, including the dy, and everything with t's, including the dt, on separate sides of the equation. So I'm going to rewrite this. So I will have 1 over y dy equals 0.05 dt. Just divide both sides by y and multiply both sides by dt. And so the whole purpose of doing that is that now I can take the integral of both sides. Oh, yeah, you can just write dy over y. That's fine. I just thought it would be easier to recognize an antiderivative of 1 over y. What is an antiderivative of 1 over y? ln y. Yeah. An antiderivative of 0.05 dt? 0.05 t plus c. Technically, there's a plus c on both sides of this equation, right? So this would be ln y plus a constant, and this is 0.05 t plus another constant. But then I could just subtract c1 from both sides, and c2 minus c1 is just some new constant, because all of the constants are arbitrary. I'll just call that combined constant c. All right, so now I have this equation, but remember the solution to the differential equation is a function. Y of t equals some stuff with t. How do I solve this equation for y? The antiderivative of 0.05. Raise e to both sides. Yes, you raise e to both sides. So this becomes e to the ln of y equals e to the 0.05 t plus c. Well, what is e to the ln of y? Y. That's the definition. That's why we did e to the both sides, because those two functions are inverses and they undo each other, so you just get y. I'm going to do some fancy magic here. We have e to the 0.05 t, and that's times e to the c. Is that true? Yeah, so because when I have like bases, you would just add the exponents. So if you have added exponents, you could rewrite them as multiplying like bases. And then I did that because e is just a number, right? 2.718 raised to some arbitrary constant is a new arbitrary constant. So I could call this like k e to the 0.05 t. So that's my solution to the original differential equation. And does that look like the function that you would have immediately jumped to from like a college algebra or pre-calc class if I had given you this same information? Yeah, you would have used 0.05 as your continuous growth rate, would have been e to the 0.05 t. What is k? That's your starting value, yeah. In order to find out what k is, you would have to have some initial value given. So this is a general solution. You need an initial value to get a particular solution. All right, so I was tired of typing the phrase differential equation, so I typically use the abbreviation ODE for ordinary differential equation. And I might also abbreviate initial value problem as IVP. Gone acronym crazy. All right, so one more separable ODE IVP together. So I have dy dx is equal to y squared plus xy squared. It's a first order differential equation because there's just one first derivative in there. If I want to solve it using separation of variables, I need to collect everything with y's together with the dy and everything with x together with the dx. So the first thing I should do probably is factor out this y squared. And then I'm going to move my dx over here so that I have my 1 plus x dx together and divide both sides by y squared. So this is going to become y to the negative 2 dy equals 1 plus x dx. Everybody follow how that works? All the y's plus the dy have to go together. All the x's plus the dx have to go together. And you just treat dy dx like a fraction. And why did I write that as y to the negative 2 instead of, say, 1 over y squared? Yes, because I'm going to use the power rule. So I thought it would be easier for you to recognize how to take this antiderivative if I wrote it that way. All right, so now I'm going to take the integral of both sides. The antiderivative of y to the negative 2 would be negative 1 over y. You have to increase the exponent by 1, so you get y to the negative 1, and then divide by that same exponent, and then that would just simplify to negative 1 over y. So maybe I'll rewrite it like that. Negative 1 over y equals antiderivative of 1 plus x plus x squared over 2 plus c. And then I get to solve this thing for y. So what should I do? Yep. Multiply both sides by y, and then divide everything by the new coefficient on y. So I'm going to get negative 1 equals y times all that, x plus x squared over 2 plus c, and then divide by that coefficient on y, x over all that stuff. Like that. So we get y equals negative 1 over x plus x squared over 2 plus c. So that's my general solution. That's my family of functions. Any function from this family will satisfy the ODE, right? Then if I want to find the particular c, I have to use the initial condition that y of 1 equals 4. So now I plug in a 1, and I get negative 1 over 1 plus a half plus c has to equal 4. And I'll just solve for the c. Keep scrolling down here. All right, so this is negative 1 over 3 halves plus c equals 4. I'm going to multiply both sides by the denominator, and I get negative 1 equals 4 times 3 halves plus c. So negative 1 equals 6 plus 4c when you distribute that 4. And then solve for c, and you get negative 7/4. So that, when you put that c in here, that is your final solution. Replace that c with a negative 7/4. So my final answer is y equals negative 1 over x plus x squared over 2 minus 7/4. That is the function that satisfies the ODE and the initial value. Okay, separation of variables is a very limited technique, right? Which is, we just use that technique on these two, where you have to put all the x's with the dx, all the y's with the dy. It's handy, but it's a limited technique. It doesn't always work. If I look at dy dx equals x plus y, right? How do I get the x's together and the y's together? Right, so, well, I have an x on the right, right? So maybe I multiply both sides by dx. So I'd have dy equals x plus y dx. Now there's no way to move the y, right, without moving a dx also, right? I'd have to distribute the dx to divide by y dx, and then I put a dx back on the other side. There's no way to separate this. Okay, so you have some time to try a few, and also if you want to go back and discuss your test some more, this would be a good time to do that also.